Good day, everyone. My name is Hulisani Madima. I'm a process engineer at Multotec Process Equipment. I will be taking you with the presentation of the mechanically agitated hopper, Model 1, which is process and mechanical training. The purpose of this model will outline the following. We will explain the segregation in between primary and secondary sampler. We'll touch on the unique circumstance shortcoming of earlier air-agitated hopper, whereby we'll also talk about the flotation of fluid product with air mixing and also lowering of fluid density that promotes segregation in unique broad range of settling velocity slurries. We will also discuss the features, advantages, and benefit of mechanically agitated hopper, whereby we will discuss the domex shape, vertical sides, VSD control agitator and baffles, minimum fluidization air collar, ATS knife gate valves, dual inspection lid, press screen, and slide out agitator maintenance slot. The other purpose we will discuss is the linear proportional of the time-based sampling, and also the control instrumentation and mitigation, whereby we will discuss the increment counters, also the level sensors, how they prevent overflowing and sample loss. We will also touch on the minimum level retention to prevent solids hang up. We will touch on air flow close off to prevent sample blowout and solid hang up. And finally, we will discuss the semi-automated flush cycle to clean, surface, and retain solids part of the shift into the sample. Subsequent to the last part of the purpose is the control philosophy and operational training model, which will be discussed by or presented by Guillaume Dutoy. The first topic that we are going to talk about is the slurry sample segregation between the increment. This is well known from sampling publication that segregation is a major error generator in sampling and a very real risk in slurry sampling. Segregation do happen of slurry between the primary and secondary sampler, whereby the material is being sampled by the primary sampler, and when it's fed to the secondary sampler, there's some settling of material and segregation to happen there because there's no mixing. In this presentation, we have also included the YouTube links, which one can go on YouTube and visually understand the mechanism of slurry sample increment segregation. So we have the link for a Londa sampler and also a link for a twin one. So the second topic we are going to discuss is the unique circumstances shortcomings. The traditional air-agitated hopper are used to suspend the slurry increment, attempt to homogenize it, retain it, and prepare it for downstream subsampling. By downstream subsampling, we mean if ever there's a primary sampler which is collecting a primary increment and feed the secondary sampler, whereby the secondary sampler is going to subsample the primary increment which is coming from the primary sampler. Those traditionally air-agitated hoppers have their unique shortcomings as well. And those shortcomings are being unable to keep all particles of varying size and densities in suspension inside the hopper. Subsequent flotation of fluid product introduce segregation instead of homogenizing material. Air introduction results in low fluid density and promotes segregation between a relative difference of fluid and solids. So the mechanically agitated hopper that we are discussing or that I'm presenting about consists of an agitator, whereby that agitator is used to stir material so that we can have continuous mixing inside the hopper. With that being said, the stirring mechanism, whereby the material is being stirred and the material is being mixed, we are trying to prevent, or it will prevent segregation. Now let's talk about the features, advantages, and benefit of the mechanically agitated hopper. The mechanically agitated hopper consists of a domex shape at the bottom. This shape is included so that mixing in the center side up impeller configuration can occur. The benefit of this excellent homogenization of the slurry type, irrespective of rheology. The shape of the outlet nozzle allows minimal solids retention, ensuring that all solids have the same opportunity of being sampled. The theory itself of sampling states that all particles need equal opportunity to be sampled. The mechanically agitated hopper also consists of vertical sides. The vertical sides have the lowest probability of solid retention and allows for reproducible sampling. The mechanically agitated hopper is VSD controlled. Therefore, the topic that we are going to talk under the features, advantages, and benefits is VSD control agitator and baffles. The baffle, as you can see by the arrow, we have 3 baffles inside the mechanically agitated hopper, which are used to prevent the slurry from swelling around the cylindrical walls and allows for excellent homogenization of all slurry type, regardless of its rheology. Because all slurries varies due to their unique rheology characteristics, the agitator's operations can be finely tuned using a variable frequency drive. This is included to ensure that precise optimization can be attained for specific application. We will now talk about the agitator blade. The agitator blade, as you can see, this agitator blade can be moved down and they can be moved up according to the level of the material which is inside the retention hopper. The blade of the agitator are designed to slide up and down the agitator shaft. They are held in place with the grab screw. They are all held up with a grab screw. These features enable the adjustment and optimization of the mixing process according to the level of the slurry in the hopper. This is tailored to suit the specific application. Now we will talk about the minimum fluidization air collar. As you can see by the arrow in the picture where the air collar is. This is to enhance, or is included to enhance the reliability and availability of the equipment by avoiding blockages during operation. The hopper outlet needs to be equipped with a collar. This addition enables the introduction of a minimal amount of fluidization air, which prevents solid from settling and clogging the outlet of the retention hopper. At the bottom of the mechanically agitated hopper, we have ATS knife gate valves. An air actuator, a reliable actuator, is used for knife gate valve action. The ATS valves material of construction has demonstrated dependably holding up against the harsh wear of mineral or mining slurries. This durability leads to reduced operation expenses and enhances operational uptime. The valve actuator and the body is protected by the splash guard, which is used to prevent splashing onto the valve actuator. As you can see, the splash guard in yellow and the arrow. The splash guard also keeps the air line and feed port free from being blocked by fine solids. Now we will discuss the dual safety lid. The mechanically agitated hopper consists of a dual safety lid to prevent a person from inserting his or her hand while the mechanical agitation is in operation. The mechanically agitated hopper consists of 2-stage access of dual safety lids. The first one being for safety inspection through the expanded metal mesh, whereby you can visually see if there's blockages inside the mechanically agitated hopper without opening the entire The second one being full access for maintenance events, which is locked. This one can be locked so that you don't gain access while you're just visually checking if ever there's a problem inside the mechanically agitated hopper while you're not doing maintenance. We also have the stress screen inside the mechanical agitated hopper, which remove incoming contaminants to prevent hopper components blockages. The stress screen can be removed, cleaned, and then inserted back inside the mechanically agitated hopper so that it can do its duty of removing contaminants. The agitator, which is inside the mechanically agitated hopper, can slide out for maintenance purposes. Slide out agitator maintenance slot allows agitator and shaft maintenance while the hopper body stays in situ. This is included to minimize maintenance and replacement time and also optimize availability of the mechanically agitated hopper. The mechanically agitated hopper is made out of 304 stainless steel. And this stainless steel offers a resistance to a broad spectrum of expected chemicals and is designed to withstand abrasion. The reason why we have 304 stainless steel mechanically agitated hopper is to enhance its longevity and helps in preserving smooth surface to avoid the build-ups of solids. There is different size available that we have for the mechanically agitated hopper, which is the 60 liter, 100 liter, 150, and 250 liter. The available size are suitable for up to 5,000 cubes an hour slurry sampling application, whereby mechanical agitated hopper is part of 3 or 5-stage sampling system. The fourth topic that we are going to discuss is the linear proportional of the time-based sampling. The following formula explains the linear proportional of the flow rate on the sample increment. By the sample increment, we mean the sample which is collected once the primary sampler goes through the stream and takes a cut. In order to calculate the volume that have been collected with one cut of the sample of the sampler going through the stream, we need the flow rate that's running through the stream. We multiply the flow rate by the width of the cutter. The width of the cutter need to be 3 times nominal top size of the material. For the slurry samplers, mostly the minimum cutter that we have for the cross stream, it's 15 millimeters. And then for the linear is 10 millimeters. Usually in slurries, we are running microns, whereby it always complies to the 3 times nominal top size, which is required. In order to finalize this calculation, we also need the speed of the cutter going through the stream, and the speed of the cutter must move at a constant speed at all times. Therefore, in conclusion of the formula, VI, which is the increment volume in liters, is equals to Q, which is the flow rate, and cubes an hour, multiplied by W, which is the cutter opening, divided by 3,600, which is the unit correction factor. They also divided by the velocity of the cutter. If production flow rates varies, the increment volume to the hopper will vary proportionally, and therefore possess a risk of the hopper capacity and the number of increment required to fill it without overfilling the retention hopper. Now we're going to talk about the controls and operation, whereby we'll discuss the risk, mitigation, and instrumentation. The risk of a hopper overflowing because of too many sample cuts can be controlled by a counter the number of increment. The instrument that we use is increment counter, which is H1C1 and H1C2. The instrument that I'm going to be discussing here will be discussed in further details by Kilom Tutoit. The second risk that we have is hopper overflows from too large increment volume. Here we need to empty the hopper through the vessel when it gets too full. We use a level detector or a sensor at 90% level. When the material reaches 90% level, then it's gonna drain the material into the secondary vessel sample. The other risk is when a hopper to have too small increment volume. Therefore, we need to select a larger hopper. This can be done by doing process calculations and sample mass balance during design phase. Another risk is slurry rheology changes and mixing not sufficient. We need to change the mixing energy, introduction of or via impellers. The instrument that can be used is VSD in the hopper. We need to install a VSD in the hopper there. The other risk that we have is slurry rheology changes and mixing not sufficient. We can control this by changing the mixing flow regime inside the hopper. Our mechanically agitated hopper have the movable agitator impeller. So we need to include the movable agitator impeller to deal with that problem. Another risk is agitation energy not sufficient to suspend coarse solids. Here we need to change mixing direction, and the instrument is to ensure that impeller rotates the right way around. A hopper drain, but some solids remain behind on the flat domex shape. The control here, do not completely empty the hopper. So the hopper must not be completely drained. You must leave some material so that the agitator blade can still be inside the slurry, and that will allow one mixing blade in the slurry to be able to mix the material which is still remaining at the bottom. The instrument or feature that we use there is the level sensor at 30% to close knife gate valve at this level and allow mixing. So when material gets to 30%, the knife gate valve closes and draining stops so that the last plate can be inside the slurry to allow for mixing. The other risk is slurry blowout by fluidization air, and we control this by closing the fluidization air when the hopper is actively drained. The instrument or feature that we use there is solenoid valve that will be closed at the air collar. So we close the solenoid valve. The other risk is all solids must drain out of the system at the end of the cycle. We do that by opening knife gate valve and flush out any solids from the hopper internals. The instrumental feature is flushing cycle with optimum wash water duration timer for various slurry stickiness. The other risk is the hopper is at 90% level and another increment is taken by upstream sampler. The control is to interlock the primary sampler to pack when the hopper is draining. The instrument or feature is to include process interlock in control system. And when the knife gate valve is open, the process interlock is enabled. Air pressure is too high, causing blowout or splashing. We control that by airflow to collar with a regulator. And then we need to add a regulator in the supply line. Another risk is when foreign or two coarse material blocks the hopper outlet. We need to remove the material or the foreign material. This is done by installing the trash screen in the hopper inlet. Another risk is unsafe inspection when opening the lid. We need to allow inspection grating that prevents body parts from entering the housing. The feature or instrument is double expanded metal mesh lid, which is included in our mechanically agitated hopper. The other risk is when the operator does not collect sample bucket on time and the bucket overflows. The control is to stop the system after a set period. And that can be done by using or installing a timer bucket full in the control panel. Another risk is when the hopper empties without subsequent sample running. We need to let the sample run before or after hopper valves is actuated to open or close. An instrument or feature, the moment the knife gauge valves open, the vessel sampler will start running. When the knife gauge valve closes, the vessel will continue to run for 5 seconds using a vessel duration timer. This concludes my presentation on Model 1 about the mechanically agitated hopper. Thank you for your attention.